This is third lecture of module 3. The module 3 is review of matrix algebra. So, in this lecture we will discuss solution of linear system of equations. Solution of linear system of equation can be achieved by direct or iterative methods. So, direct methods actually consist of Gaussian elimination, which probably all of you know, Gauss-Jordan elimination, which we have discussed in the last class in the context of matrix inverse, and also we have discussed it for solution of linear system of equation. And there is LU decomposition. LU decomposition is very popular. Cholesky decomposition, QR decomposition, these are more or less the direct method of solutions. And another kind of method where the full matrix is not factorized, or method like Gaussian elimination or Gauss-Jordan methods are not used, is the iterative way, methods, where we solve the system of linear equations in an iterative manner. So, these kind of methods is very suitable for large scale of system, the iterative methods, which does not required in this course. But it is very important to know what kind of iterative methods are there. So, for instance, the Gauss-Seidel method, Jacobi method, SOR or successive over relaxation, conjugate gradient, and then several other types of method, minimum residual method, GM, RES, generalized minimum residual methods, and all other things. So, we will not discuss the iterative methods, we will discuss here mostly the direct techniques or direct methods of solution of linear system of equation, of which we have already discussed the Gauss-Jordan, and in this lecture we will discuss about the Gaussian elimination and the LU decomposition mostly. So, the Gaussian elimination all of you have known, but before Gaussian elimination let us little bit investigate on the how we can easily solve triangular system of equations. For instance, if the coefficient matrix is a triangular matrix of this form, this is an upper triangular matrix, and this matrix with a vector x1, x2 and x3 with the right hand side b1, b2, b3, we want to find out the solution of x1, x2 and x3. So, if you look carefully that if that x3 is directly obtainable by just dividing by a3. So, once we know the x3, then from the second equation actually if we substitute the value of x3, and then we can directly find out the x2. Similarly, with the help of x3 and x2, we can find out x1 from the first equation. So, you see this kind of substitution is first we compute the x3 and then x2 and x1. So, it is the backward way of solving the or finding out the solution. So, this type of substitution is known as backward substitution. Now, if there is a n cross n matrix which is an upper triangular, and then you have n unknown variables or n equations which can be written in a upper triangular form, then the generalized formula for the backward substitution is this, which we can easily write for the backward substitution formula. So, now similarly a matrix can be lower triangular also. So, if it is lower triangular, then the process is just reverse. Instead of proceeding from the last variable, we proceed from the first variable. So, this is a kind of lower triangular matrix where the upper portion of the matrix is essentially 0 and then this lower part is non-zero. So, it represents again 3 variables, 3 unknowns, 3 by 3 matrix, and then here what we do, we first estimate the first variable x1, which is essentially b1 by a11, and then again compute with the help of x1, we compute x2 and then x3 simultaneously. So, this kind of substitution, if you look carefully, this is the forward progression or forward substitution. So, if again the general formula for this is this. Now, if you look carefully, the even the backward substitution and forward substitution, now you see you are actually dividing by this a11, a22 and a33. Now, if one of the these values are 0, then the procedure will obviously break. Now, so we have to ensure one thing, that these diagonal entries by which we are dividing the right hand side of the solution is actually should not be 0. So, if it is 0, then our procedure will break. So, this actually leads to an important concept called pivot, which will be used in the Gaussian elimination. So, let us start with the Gaussian elimination. The main idea behind this method is to reduce the solution of general system of equation whose coefficient matrix becomes triangular matrix, because triangular, once we obtain the triangular matrix, the solution is very simple, either backward substitution or forward substitution. So, the goal is to convert the coefficient matrix to a triangular matrix, but we have to keep in mind that the diagonal non-zero diagonal elements, we have to ensure that the diagonal elements are not 0. If it is 0, then our backward substitution or forward substitution will fail. So, as we have seen in the last slide. So, once the coefficient matrix becomes triangular, lower or upper triangular with non-zero diagonal element, we can use the forward or backward substitution to find out the solution. So, basically the goal of Gaussian elimination, this method, Gaussian method of solution, is to make the coefficient matrix triangular. So, with non-zero diagonal element. So, let us see with an example which we have solved for the Gauss-Jordan method elimination. What we did is actually we made this coefficient matrix is the identity matrix, and through the row operation. But here we will not go till the coefficient matrix becomes identity matrix. Before that we will stop. Let us see. So, here the 3 variable and 3 equation, the matrix vector form of these equations are of this. So, this is the coefficient matrix A, and with the Gauss-Jordan elimination we have learned last class is that we write the augmented form of the matrix with the right hand side of the vector as the augmented part with the coefficient matrix. So, here what we do the row operations. So, these row operations, the first row operations are R2 minus 2 R1, that is R2 is substituted R2 times R2 is minus 2 times of R1. So, if you do these row operations, then matrix changes, and as well as the right hand side also changes, and similarly like this, if we perform the row operations, we obtain this kind of triangular system. So, in the Gauss-Jordan process, we further did the row operation, so that the matrix becomes this coefficient matrix becomes triangular, but we stop here, because if we look carefully, our converted or the changed matrix is a triangular matrix. So, now we can use the for backward substitution, this is the general formula for backward substitution. Now, if we use the general backward substitution formula to find out the solution of x1, x2 and x3. So, Gaussian elimination is essentially connected with the Gauss-Jordan elimination or Gauss-Jordan process, in which we stopped early once we reach the triangular form of the matrix. Now, but let us see a complicated example where we have a 4 equation and 4 unknown. So, here what is important, we will learn actually what is the pivot. Now, if you see carefully, this matrix is my coefficient matrix. So, again as in the previous case, we write the augmented form of the matrix, and this augmented form is actually written here. So, now here again we do the row operations. So, what is the objective here? The objective is here from the second equation, if we can remove the x1, and then from the third equation if we can remove x1, and fourth equation if we can remove x1. Similarly, from the third equation if we can remove x1 and x2, from the fourth equation if we can remove the x1, x2 and x3, then we can just find x4 directly. So, keeping this in mind, so our objective is to remove the x1 variable from the second equation, third equation and fourth equation. To do that, now if you see, if these two, if I subtract 3 by 2 times of row 1 from the row 2, we obtain this row 2 with 0 in the first element of the row 2. Now, similarly, if I do 1 by half times of R1 if I minus 1 by half R1 from row 3, we obtain 0. Similarly, 1 by half of R1 for R4, if we minus, then we get 0. Now, if you look carefully, these operations are why this term 2 is coming. So, if you look carefully, this first entry of the coefficient matrix A11 is actually the second 2. So, this term is known as the pivot. So, this is very important term or the very important element of this pivot. So, this 2 is playing a great role in reducing this matrix in a triangular form. Now, in the second case, now once we obtain x1 is removed from second, third and fourth equation, now our next objective is to remove x2 and x3 from the third and fourth equation. So, if I want to remove x2 from the third equation, then we have to again look for the pivot. Now, you see the pivot here is 0. So, again this once we reach a 0 pivot, this procedure will break. Now, so here we do as we did earlier for the Gauss-Jordan case, we swap the row. So, we swap the row 2 and row 3, so that we do not encounter with the 0 pivot. So, here we swap the row, we interchange the row or row exchange we did. So, that the second or a 2 element of that matrix becomes non-zero. So, here we obtain this 3. So, our new pivot will be 3. Now, with this 3 again we do the row operation. If you look carefully that by row exchange, it is already this x2 is removed from the equation 3. So, we have to remove x2 from the equation 4, that is 4th row. So, again we do 1/3 times, we subtract 1/3 times of R2 from R4, then we obtain this matrix. So, if you look carefully that from the third equation and fourth equation, x2 and x1 is removed, and then again we look for the pivot, which is 7 here. which is non-zero. So, again we do row operation to remove third variable from the fourth equations. So, again if we use 2/3, if we subtract 2/3 by 7 times of R2 from row 3, row 4, and then we obtain the final triangular form of this matrix. So, if you look carefully, this form is a triangular form. Now, once we reach the triangular form of equation, then our solution procedure is very simple, and this is a upper triangular form. So, you use backward substitution to find out the solution of variables x1, x2, x3, x4. Now, here you have to look carefully two things. So, one is our objective is to make the coefficient matrix triangular, and second, we do not encounter with 0 pivot, because if we encounter 0 pivot, the procedure will break. So, what is the solution for that? We do row exchange or row interchange, so that we do not encounter the 0 pivot, as we have seen in this example. Now, this is overall Gaussian elimination. It will be very helpful for us to use this method for the matrix structural analysis course. Now, another way of solving this linear system of equation is LU decomposition. So, LU decomposition is essentially a matrix is decomposed in two submatrices or two matrices, which is of L, the lower triangular matrix with diagonal element 1, and U, the upper triangular matrix with the lower part of it 0. So, for matrices all of whose diagonal submatrices of order k are non-singular, these kind of matrices can be decomposed through LU decomposition. What does this mean? Actually, if you look the meaning of this sentence is this: if it has to be A11 has to be greater than 0, and the A11, A12, A21, A22, this submatrix has to be greater than 0. The determinant of this submatrix has to be greater than 0. Similarly, the total matrix, the determinant is has to be greater than 0, because if the matrix is the final determinant, the whole matrix determinant is not greater than 0, then we will be reaching to the non-singular system, singular system of equation, for which the matrix inverse does not exist, what we have learned in the last class. Now, if you use this kind of decomposition, so finally, if you multiply these two matrices and write it in this form, then we will see the how to calculate these L ij's and U ij's. So, if you now compare these two matrices, from this previous slide, this U11 and A11 should be same. So, U12 and A12 should be same, U13 and A13 should be same. Similarly, A21 we can write is L21 U11. So, once we know U11, L21 we can directly find out by dividing with the A21 and U11. So, similarly, U22 we can find out, which is essentially A22 minus L21 and U12. So, you see this L21 is used in finding the U22. So, there is a sequence, you just directly cannot find out from the last entry U3. So, you have to come up from the forward sequence. So, the first element, then 1 2 element, then 1 3 element, and so on. So, so once we do this, we find out all Lij's and Uij's. So, once we do that, so this is the generalization we have seen for the 3 cross 3 matrix, which is a which can be generalized for any dimension, means n cross n matrix, and this generalization is how to do it. So, this is the formula for the generalized n cross n matrix. So, this is very helpful in coding, because if you want to code it in a computer, you need to use this kind of formula. So, here if you see carefully, these LIP and UPJ, these terms are dependent. So, finding out UIJ is dependent on LIP, where I is where J or the P running from 1 to I minus 1. So, this is important. So, once you code it, you will see that it is sequential, as I was talking about in this, that you just directly cannot find out U33 from in a first step, because to find out the U33 you need to know L31 and L32. So, to find out L31 and L32 you need to finally know the U11 and U12 and U22. So, all those things you need. So, once you find out the U and L, the solution is very simple. Let us see what is the solution. The solution is, so we decompose this matrix A in LU form. So, if I write the matrix equation, AX is LUX. So, LUX will be B. So, my new equation is LUX equals to B. Now, if we assume UX is Y, then LY equals to B, because if I substitute UX equals to Y here, and then LY equals to B. Now, LY equals to B means we have to find out the y. So, again you see this is a lower triangular system where we use the forward substitution to find out the y1, y2 and y3. So, once we know the y1, y2, y3, the second part ux equals to y, the y's become goes to the right hand side. So, our job is to find out x1, x2 and x3. So, once we once we find y1, y2, y3, again this is an upper triangular matrix. So, we use the backward substitution to find out x1, x2 and x3. So, in this way the LU decomposition can be used to find out the solution of system of equation. So, next let us see an example. So, if there's this is a just the previous example. So, this is just the LU form of the coefficient matrix A. So, if you look carefully, that in the Gaussian elimination we were obtaining the same form of the triangular matrix through the using pivots and row operations. So, if you look now these two procedure, that this L matrix is essentially consisting of these pivot elements, the pivot multipliers, the multipliers which we subtract or which we use to make the row operations, and finally making the matrices upper triangular. So, if you see, these L consist of all such factors, and U consists the matrix which is finally we obtain. So, but we do not change the right hand side here. So, we keep the right hand side original with the B. So, again this Ly equals to B and Ux equals to y. So, the right hand side is actually Ly, this y is the changed right hand side, which will be obtained by solving the Ly equals to B. So, there is a connection between the Gauss elimination and LU decomposition. The Gauss elimination is actually using the row exchange and pivoting operation, but in an LU decomposition you obtain this pivoting through a decomposition procedure. So, or the factorization procedure. So, there is a connection between these two methods. Now, another important thing is that LU factorization actually preserves the band structure of the matrix. So, this is very important because we will be using the banded matrix mostly for the structural analysis, because on the stiffness matrices when we will be assembled it will be in a band format. So, if the banded matrix if we do the LU decomposition, its banded form is preserved in L and U matrices. If you look carefully, this is a banded matrix, and if this the diagonal elements remains 1 in L and the first band is non-zero, the other part of the matrix or the other elements of the matrices are 0. So, keeping in mind that this band form is very similar to the original matrix, because since this is a lower triangular matrix, so upper part has to be 0. So, only the first band or the first diagonal form is the important here. So, similarly, in the upper triangular matrix, the diagonal elements are non-zero, and the upper part only one entry is in the band. So, this structure preserving LU decomposition is very important for us, because as I have said already, that we will be using mostly the banded matrix. So, that is all for today. Thank you.